somebody said they are not mutually exclusive. So let me tell you that right now we are talking about only activating marks. So there are examples where the activating mark is actually coming along with inactivating mark. So there are multiple valencies out there. Okay, do you know the example if it is taught? There's something called bivalent marks. Do you know about them?
Yes, sir.
Yes, no.
Yes, sir.
Okay, so the bivalent marks. Okay, what is it that we are talking about? So bivalency gives some kind of bistability to the system. Okay, so what do I mean by bi? So let me give you. So there's only one known so far. Maybe in future we do learn about more bivalent or multivalent marks. So the example is the following. S3 K4 methylation comes along with S3K27 methylation. And you already know that this is a repressive mark, particularly associated with polycomb group of proteins, right? Polycomb silencing of development of genes, and this is activating mark, right? Now this only happens at promoters. They come together. So what we are trying to say is, let's say that you have a gene over here, and when we talk about histones, right? So let's say there's a stone tail out there. So it has S3K4, K4. So this protein was S3, so K4 trimethylation, and K27 trimethylation. This same histone, okay? And you have, let us say, this is downstream. You have your gene, okay? And this protein was this was S3 protein. Well, this is not S3. There will be S3 over here, right? And you will have S2 also over here, and two of each, right? S3 and S4, sorry. Right? So there will be four of such, four or eight. How many are there in the nucleosomes? A total eight of these, right? Eight. If you look at three-dimensionally, they will be here. So on H3 protein, we have these two methylation coming on the same H3 molecule. That's what the claim is. Now, what can be the problem here? Let's say that can it be a fluke thing? Let us say for the time being, imagine that this is fluke. I don't think it is a fluke, but let us say it's a fluke, which means that there's a mistake in understanding this. There's a mistake in identifying these things. So what could be that? How do we identify these? We look at what we do an experiment on millions of cells, right? We take millions of cells, isolate chromatin, and do the chip experiment on that, right? So how do we know that K4 and K27 is coming from the same cell? So let's say the possible issues. I'm not saying that this is not true. Now people are working on single cell, and I think they have shown it there. It's present on in the same cell. Possible issues is that they could be coming from two different cells. So let's say there are some cells over here and some cells over here in the whole population of cell from which you have done the ChIP-seq. So in this cell, a particular promoter had the K4ME3 methylation, while in the other cell it was K27 methylation. Right? So forget about these cells. So there's the whole population of cells. So I just gave you the example of these cells, right? Okay, so there could be heterogeneity of the cell population, but this is the same locus. The gene here is A. This gene is A gene, and we are looking at A gene only. When we map the data into genome, we only look at the promoter of A gene, and once we pull down the data into one table or one plot, we learn that this promoter is having both the marks, but how do we conclude that they are coming from the same cell? So that's one issue, right? So single cell can resolve this. What can be the other issue? Let's say that now people have said that they are coming from the same cell. Let's say there was one cell like that, and it's coming from the same cell. Now we know that yes,
The same stone and the
that will also come. That will also come. But I think people can resolve that by resolution. That we have two chromosomes, right? Maternal and paternal. So, okay, by the way, most of the things that I will be talking in this course, in my part, would be actually mammalian genome. Okay, I wouldn't be going to the lower. In some cases, I might go, but mostly I will not go to the eukaryote like yeast. Right? So it might be the case that one of the allele was actually K4 ME3, and the other allele was K27 ME3, right? Which is repressed allele. And somebody else mentioned that the different histone, right? So it could be like that. So in one case, I have K4 ME3. In another case, I have K27 ME3. However, this can be resolved if your resolution is really high, genomic position, right? This is how much 156 base pair apart, right? So if your resolution, and generally we do get big resolution these days, so this can be resolved by resolution, right? So this can be, let's see how things can be resolved by resolution, by sequencing resolution. How can we resolve this thing? Resolved by allele specific mapping sequencing, right? Allele specific sequencing. If you know what were the paternal genome through which we got these cells, right? So then you know which is maternal, which is paternal. This can be resolved by single cell analysis. We do the ChIP-seq on a single cell. Okay, so I think despite doing all that thing, people do have sufficient evidence to believe that this is actually happening. Now, there was a reason I wrote about these issues, because when I was doing PhD, these things were not properly resolved, and I was in a view that more often these two are the cases. Okay, but then people came up and now we have quite a good number of evidence that in fact is happening on the same histone. Now the question is why? What is the advantage? Well, why question is a bad question in science, so we don't know why are we here. So, something that we can ask in English doesn't mean that it's a genuine question. But why, in a sense, that what is the significance? So let me change it to significance. What is the significance of having these marks? Why do we need bistability? There is a bipotential, right? Bivalency. So why do we need that? Completely contrasting thing. Okay, it can be activating and inactivating. I already gave you the hint. You tell me what could be the advantage.
To have a proper control, we should have a on switch and an off switch.
What is the proper control here?
For some protein factor would recognize the
Well, let us say both the marks are there. What will happen at the first place? K4 try to attract Pol2 and all the transcription factor for activity. K27 will bring the repressor molecules, and there will be some kind of conflict going on, right? So what is the proper regulation here? In fact, it's the other way around. There's a conflict going on. Well, I think partly I already said this. The moment I use the word bistability, I'm already talking about something that it gives you. So, if you have two marks like that, so if one disappears, the genes will be activating, right? Gene will be transported. If the other disappears, the gene will be repressed. So now tell me what is the advantage, and where do we see that advantage?
So maybe to control the amount of activation or repression, we are using the opposite thing.
Well, yeah, amount, but this will not be this will not lead to full length transcription. Okay, because there is a conflict going on, there will be some initiation of transcription, but it will not be elongated. It will be some kind of what we call as poised transcription. Okay, so let me tell you what is the advantage. Let's say that this is the tail and we have both the marks out there. Now, what happens downstream is that you have some kind of transcription initiation, but it's not completely elongating. So some kind of little bit of transcription will happen. Okay, downstream. So this is we call it as a poised state. It is kind of having bistability. Okay, it is like that. It can either be inactivated or activated. It has both the potential, right? That's what we mean by bistability, that either this will be stable. Right now, it is in an unstable state like that, fluctuating. It can go this way or that way, right? Now, these we call in biology, we call them poised. Okay, so they are poised to either go inactive or active. Now, we have these marks abundantly at the developmental loci in pluripotent stem cells. Okay. Stem cells are pluripotent, as the name writes in that way. You can have these marks in your germline stem cells, right? You can have these marks in your blastocyst stem cells and so on. Okay, and where at developmentally important loci. Okay, at the promoters of important genes like Hox genes and other genes, sonic hedgehog genes and so on. Now, can you now predict what is the advantage now of this state?
So I think like in some cells maybe the gene might be active and on other cells it might be silent. So to provide this dynamic activity, this is
No,
helping
in
it.
stem cell this is not the case. I'm saying that they are present on in the same cell, same allele, same histone. So where is the advantage?
So then maybe the phase is determining like at particular phase it needs to be
In the
silent.
what?
So at particular phase this
Yeah, so
gene
you're
needs to
not
be
using
active.
the right term, so use biological term, differentiation, right? So the moment you have differentiation of this, let's say you needed this gene in your neurons. Okay, so during neuronal differentiation, the mark has to be active one, right? So here you will have K4 methylation and K27 methylation has disappeared. Right? So now this gene will be abundantly transcribed in your neurons, where this is needed for neuron differentiation. So this is happening in your cell in your neuron. Right? There can be another differentiation pathway, the fate determination, this cell during differentiation, and there it is actually the K27 methylation. So this gene was K27 methylation. This gene was neuronal gene. Let us say that the blue gene over here, this gene is neurogenesis neuronal gene. For the sake of name, there is nothing called neuronal gene. Okay, so we don't need that gene, neuronal gene. What is the fate of neuronal gene in, let's say, skin cell, dermatocyte, right? So during the differentiation, it is not needed in skin cell, it's not needed in hematopoietic cells, not needed in mesenchymal and cardiomyocytes and all the other cells not needed. Wherever it's needed is K4 is retained and K27 is erased. Wherever it's not needed, K27 is needed. Think of another gene which is needed for your skin differentiation, then you need K4 primingylation there, and in neuronal cells, there will be K27 primingylation, right? So this is the bistability, that these genes are poised and they are ready to be, so they are not waiting that, there will be, everything will be started from scratch. They are just ready to be poised, and there's a switch going to be activated or inactivated during differentiation. So this phase over here is differentiation. Right? So that's what the advantage of, and we know almost 70 to 80% of the genes which have these marks are actually involved in that. Okay, so now what is emerging here in the previous class and in the present class is that there is some kind of combinatorics going on, right? And this combinatorics, just wait, Vishnu, sometimes it's redundant. Many of the activating marks are coming together, right? And inactivating marks are coming together. So, and we learned that it could be important for robustness and cooperative binding, number one. Number two, sometimes they are contrasting. Okay, so various combination like the bivalent marks. Okay, and sometimes they come in a combination which demarcates one element from another element, like promoter and enhancer are demarcated by differential enrichment of these marks, right? So these combinatorics we already knew for a couple of decades that there's some kind of combinatorics is happening around. But only recently we were having, in last 5 to 10 years, we were having genome-wide data sets, and for number of histone modification in different cell type, different species, now we can study that combinatorics and define the chromatin types more precisely. Okay, to tell that I don't want to look at the 20 histone modification to say something. It will be difficult to interpret. I can decide maybe 5 to 7 chromatin states. Let's say active and active promoter, poised promoter. Poised promoter is this one only, right? These are poised promoters. Active promoter, poised promoters, and then strong enhancer, weak enhancer, and then heterochromatin, and then polycom repressive domains, insulators, and likewise. Right. So we will see in the next class that how do we actually do this with the genome-wide data to use this combinatorics to define various different chromatin types. Okay, so Shruti had a question. What happens to the gene when both marks are there? Is it active or inactive? This is poised. Vishnu, you had a question.
Yes, sir. So with this advantage, can we say that the tissue-specific genes are having this bivalent chromatin, housekeeping genes are not having? So
Yes, yes, we can say this.
is it completely true? Like all the housekeeping genes are not
All the
bivalent?
housekeeping genes will be devoid of this. Yes. Now, of course, biology is having exceptions, right? So somewhere you will find that surprisingly that there is, a couple of exceptions out there for some reason or some noise or some repetitive elements which are out there. You may have some exceptions out there, or that is actually not exception. That is the lack of knowledge that they were actually relevant for those genes in some context that we don't appreciate right now because we don't know. Right. So largely yes. So unlike physics, where if there is a law, generally there is no exception. Biology is full of exception. We revolve around the mean values, right? So if you look at the mean thing, then most of the things, most of the housekeeping genes will not have bivalent marks. Only developmental genes will have. So in fact, somebody asked, Sweetie asked that what happened with both the marks are there. I said it is poised, and that poised expression is actually noisy, as you see that sometimes there is a full length transcription, sometimes it's not there, and sometimes the gene is actually in some cells repressed, sometimes it is active. So it's all kind of noise. It actually introduces noise at those loci in the process of this conflict to keep the state poised. Okay, so in the next class, we will look at how do we define the principal chromatin types. I don't want to look at this, 20, 30 histone modifications and then various genomic elements, and this is gene body, this is promoter, enhancer. I just want to define chromatin. Chroma means colors. So can I have different colors? Red color for promoters, orange color for enhancer, green color for the gene body, blue color for insulator, and I have 7, 8, or 10 such states, and I'm done. Okay, and that state is derived through all these bulk of system modification data, just to compress the information, just to reduce the dimensions. We will see that how people are doing it. Any question? So when are we meeting then? When is the next class? Do we have exam next week?
Yes, sir.
So there's no class next week, or do we have some classes?
We have mixing from Monday, Tuesday, and Wednesday, 3 days.
Monday, Tuesday, Wednesday. So Thursday class will be there, right? Okay. So I will refer to the timetable and accordingly. So most likely there will be class on Thursday. I'll try to finish this chromatin type thing. So in the round section, what I understand, to learn about the mechanism of histone modification, DNA methylation, and all that. Now we are looking at the combination of those things and what chromatin type we can conclude to. Okay, as of now, and then we will move on that how these states are further having another dimension of higher order chromatin structure, which can influence their fate of each locus. Okay, so if there is no more question, then we stop here. I will upload these slides as MP3, so there will be no talk I will not be speaking, but you will have this slide. Once you click it, it will play the video of these slides. That's all. Very small file. So that you have some content. Otherwise, you can always refer to the books which are recommended. One of them is epigenetics. Both the name of the books are epigenetics, right? There are two books posted, and I forgot the author's name. This is one is David Ellis, right? So these are some prominent authors in the field. David Ellis is one of the pioneer in epigenetics, and then you have other authors also. I think there are a few control authors. Weinberg is also Davis Barlow, who is a prominent East epigeneticist. The other book was from another author, which is actually it's from L. Armstrong, right? So I think that is much more a brief book. Brief in a sense, just having the textbook material for the entry level students. If you are a PhD student where you want the details, how this experiment is done, how did they improve this, then David Ellis' book is much better. But for BSMS students for whom this is really very new, Armstrong's book is preferred. Some of the things that I'm teaching may not be there in these books. I'm not following any of these books. Okay? So, but these are the materials given to you for reading. Do you need some additional material from me? Apart from what is given in these slides? I can, for example, when I talk about principal chromatin types, I can give you a couple of papers on that. If you need details, now those papers will have very sufficient details, right? So they may not help you to understand the overall course, but it's one of the parts that I'm teaching appeals you a lot and you want to look at in detail, then those papers are recommended. I can post those papers if some of you want. For example, how do we determine principal chromatin? I will not go to the underlying mathematics in detail. For example, principal component analysis is used, hidden particle model is used. Some of these are taught in bioinformatics lab course, other one is taught in data science course, but this course is not supposed to have mathematics. So I'll just briefly tell that this is the way overview that I will talk about the derivations. But if at all there is a majority who wants the derivation again to be taught in this course, I can teach that, but that will take more time here if we run out of time. But I will do the survey. If there is some interest in knowing the details, then I can do so. Otherwise, following that book should be sufficient. Following these material that I'm providing will end up, of course. Okay, so I'm stopping here.